Alright everyone, welcome to another Physics 211 lab simulation. This week we're going to be having a chat about two different topics in optical physics, namely mirrors and lenses. So before you really jump into this video, please go ahead and take a look through those theory sections and make sure that you understand them before you come back. And you can go ahead and stop at the data collection sections for both of these because of course we are not taking these we're not doing these labs in person. So go ahead and take a look at those and then come back. Now let's go ahead and jump into the actual lab procedure here. Unfortunately, as great as they are, and as wonderful as Colorado has been to supply the world with these simulations, the University of Colorado doesn't actually have a simulation that corresponds to the mirrors lab that we would be doing in person. So we're instead going to be doing a bit of a theoretical discussion and a couple calculations corresponding to mirrors. So let's dive into the theory a little bit. Now, if let's say I have a plane mirror, which apologies for my drawings here, I'm not the best artist on the best of days, and using a mouse to draw on a virtual whiteboard is going to be somewhat challenging, but I'll do my best. So let's say that you've got a plane mirror, and it's basically just like a rectangular thing that is relatively extensive. Then the law of reflection states that if you've got some light, so let's say you've got a laser shining on this thing here, and you've got light coming this way. If you've got some light that's going to hit this mirror, intuitively you know that this light is going to bounce off the mirror and get reflected at some angle, right? Now, the law of reflection tells us that with respect to the normal of the plane mirror, so I can draw a relatively straight line, oh well, the law of reflection tells us that the angle of incidence, so that's going to be this one right here, oh gosh, theta I. Okay, so pretend that's a theta. The angle of incidence is going to equal the angle of reflection, which is right here. Sorry about my handwriting. In any case, the same angle at which the light hits the plane mirror is going to be the same angle that it is reflected at. Now, there's another geometric result of the law of reflection that has to do with what are called image and object distances. Now this is a little weird because let's say I place an image here, like, I don't know, a hairpin, or maybe, you know, somebody's standing here in front of a mirror and they are some distance DO, standing for the distance of the object away from the mirror. Now what's going to happen is there's actually going to be an image behind the mirror, which is a little weird. Now I'm going to mark this in purple because it's a bit different. So there's going to be an image behind the mirror, and the law of reflection states that that image distance is going to be the exact same as the object distance. Now, the weird thing is, like, let's say you had a friend standing at this blue point, and there's this big old plane mirror in a room, and you walk behind it to, you know, see that image. You're not going to see it because the light isn't actually piercing through, you know, piercing all the way through this mirror, so you're not actually going to see anything. So what we actually call this in physics is we call it an virtual image, and it's really nothing physical, but it's still there, and that's a bit uncomfortable, but we're just kind of take my word for it for now that there's a virtual image kind of behind this mirror at the exact same distance as the object distance. Now, let's just kind of dive into doing some calculations here, following section 1.1 of the virtual lab procedure. And a quick note, all of the angles referenced are going to be with respect to the normal of this plane mirror, which I've kind of drawn out here, this little black, unfortunately curvy line. Imagine that this is a straight line. And we are told to imagine a ray of light, like from a laser, at an angle theta between 5 and 85 degrees upon the plane mirror. So let's kind of just take this situation that I've drawn out here. You've got your incident light from a laser at an angle theta I, and it's telling us to pick one between 5 and 85 degrees. So just for the sake of argument, let's pick theta I equals to, I don't know, 77 degrees. 77 is a good number. And it says to use equation 1 to calculate the angle at which the image of the laser would appear to an observer who is positioned 5 centimeters away. Now, again, we're imagining that let's say we're 5 centimeters away here, and the source point is also 5 centimeters away. So like we got a source point here, and that, like, let's say this is constantly shining laser light over here, and you're standing, I don't know, right, 5 centimeters away as well. Now, what we are asked to do is to calculate the angle at which we would see this light coming off of this mirror. And if we're using the law of reflection, which is this one, so delta theta, let's calculate that, is equal to, it says theta reflected, which we're trying to solve for, minus, in this case, the incident angle, so 77 degrees, is equal to 0. And by advanced methods, that means that the reflected angle is going to equal 77 degrees. So just by the law of reflection, we're standing here, we're standing over here or viewing it from over here. There's an image, so a laser that is being shown on the mirror, and it hits the mirror at an angle of 77 degrees, gets reflected at that same angle. And now it says to enter the angles from parts 2 and 3 found in the data tables found in section 3, which is all the way down here. So if I were doing this on actual paper, I would be writing down the incident angle as 77 degrees and the reflected angle as also 77 degrees, as I've calculated here. Finally, it tells us to repeat steps 2 through 4 times with the other theoretical objects, placed at different angles between 5 and 85 degrees. So I'm not actually going to go through that part now. You can do that on your own, but essentially just pick 4 other random angles between 5 and 85 degrees that are different from 77, and enter those and their respective reflected angles into the other entries on this data table here. Alright, so once we've done that, let's move on to the object distances. And this is going to be extremely similar, only we're not going to be dealing with physical images anymore. We're going to be dealing with virtual images, and we're not dealing with angles anymore, but we're dealing with distances. So like I mentioned before, if you've got an object placed in front of a mirror at some distance d0 or do away, that is going to have that's going to produce a virtual image behind the mirror at that same distance di away. And to simplify things, let's imagine that we're all standing, that we're not kind of viewing this from an angle here, right? Let's imagine that we're viewing it kind of straight on, okay? So the lab manual says, imagine a plane mirror placed at 0, so we're calling this little axis here x equals 0, and imagine you place a thin object at a distance between 2 centimeters and 10 centimeters away from the mirror at an angle theta I with respect to the plane mirror's normal. So let's say I'm placing it here. So this is my object, and let's call this distance, I don't know, 5 centimeters. So 5 centimeters is our object distance. Now it says to use equation 1 to calculate the distance at which an image would appear in focus to an observer who is positioned at an angle theta r equal to theta I, so the same angle that this is at with respect to the plane mirror's normal. And of course it's implied here that the image actually would not appear to an observer who's in front of this mirror, and you also wouldn't see it behind. But again, I'm kind of just asking you to get a theoretical idea for what's going on here. So imagine, you could actually see this image behind it, but remember you can't because it's a virtual image. Then at what point behind this mirror would you see it? So we have some, image distance behind here at some distance di. If you use the law of reflection that we just used before, that says that the delta d is equal to d0 or do minus di, and that's equal to 0. So again, we have our object distance at 5 centimeters. So 5 minus di is equal to 0. And again, by advanced methods, that means that di is equal to 5 centimeters. All right, so once we've done that, you can go ahead and head down to the data tables again and just enter those object and image distances in the table here. And again, it says to repeat that 2 through 4 times, each with different distances between 2 and 10 centimeters away from this theoretical mirror. Again, I won't do those just because I feel like it'd be a bit redundant, but please go ahead and make those calculations and enter those in these 2 respective tables here. All right, so now we're going to get into the meat of this simulation, which is the thin lenses portion. Sorry about that rough break in editing there, but I had to step away for a moment. So we are back with the part 2 of this simulation, and we're going to be talking about thin lenses in this portion. But let's get started by having a little bit of a discussion about the difference between converging and diverging lenses. So a converging lens, which you can kind of see here, is this kind of convex sort of shape. And what if you have an image on this side that is producing light rays, they kind of spread out as the further along you go, as denoted by these white lines here. But as they hit this converging lens, a converging lens will take them and refocus them at some distance away, which is going to be over here. And you'll also notice that it is a property of converging lenses that they flip the orientation of the image that you're looking at. So here in the object, the pencil is face up, but over here in the image, the pencil is face down. That's because this light ray traveling over here hits the converging lens and then gets turned around, refracted the same general direction it was going, but sent downwards now. And here, this one that was going downwards is now going upwards. And so you get this kind of flipped image. Now, that's a converging lens, but let's talk about a diverging lens. A diverging lens is essentially the opposite. It's kind of got this concave look to it. And that's an awful drawing, but I'm sorry for that. But let's say you've got a source point here of some light, and its light rays are hitting the converging or diverging lens, sorry. What it's going to do is this diverging lens is going to take these rays. I'm going to draw a couple more in there. And it's actually going to spread them out even further than when they came in. So, like so. So what it's going to do is it's going to spread those light rays out as opposed to focusing them some distance over here. Now, in this experiment, we're not going to be dealing with diverging lenses. We're going to be dealing with converging lenses, just to make things a little simpler. Now, moving on to some definitions and equations. Here, this letter P denotes the distance between an object and a lens. And this letter Q denotes the distance between a lens and its image. So the image is denoted x sub I, the object is denoted x sub O, and then the position of the lens is denoted x sub C. Now each lens has its own focal distance, which is denoted by F, and you can calculate that by taking the inverse sum of 1 over Q plus 1 over P, just solving this algebraically for F, and then going from there. So if you know Q and P for a specific scenario, you can actually calculate the focal distance of a lens, which is essentially what we're going to be doing today, after doing some graphing and such. So moving on to the setup, it says that once you open the simulation, check the box that says ruler, check the box that says screen, and then make sure that the no rays button is filled in. And also tells us not to touch the curvature radius, refractive index, or diameter, because we don't want to mess with the properties of this lens as we're doing this experiment. Hopefully that should make sense. Now, it also says to move the light source all the way to the left, which we're going to do now. And we're going to call this 0, okay? So we're going to set the ruler at x equals 0, which we are basically, by doing this, setting x sub O to 0. Now, this is going to simplify calculations a little bit because it means that wherever we place the lens, so xc, the position of the lens, is going to be equal to p. So that'll make some calculations a little bit easier, as you'll see in a little bit. Now, as I go through this, make sure that you are filling in this table here, and if you wish, also this table here. I'm not going to fill them in on my own, but because I don't have the ability to write on this PDF file here. But if you would like to, go for it. What you want to do is fill these in, and then you're going to be calculating P and Q, 1 over P and 1 over Q, and then going from there. So I will kind of give you an idea of when to fill in those measurements as we go along, and then we'll speed things up a little bit after the first couple measurements. All right, so first it says to, using the on-screen ruler as a reference, move the lens to x equals 180 centimeters. So we're going to do that. And I'm going to move the middle of the lens to 180 centimeters. This is the distance known as x sub c, so enter that into the table found in section 3. So enter 180 centimeters into x sub c here. Now it just so happens that in this case, because of the way that we've set up the lamp being at x equals 0, x equals c is equal to p, so we have 180 centimeters here, and that's also going to be equal to p. So go ahead and fill that in for p as well. Now it says to drag the screen until the light focuses to a pinprick on it. You can see as I drag it left and right, the image becomes more spread out or more focused, and we want to focus it as much as possible. So we're going to focus it There we go. And then it says to click on marginal rays just to make sure that we've done a good job. So you can see we're right around where the rays recombine, so it looks like we've done an okay job. Now what we're going to do is measure the distance between the lamp and the screen itself. So from the lamp, we know that this is 180 centimeters, so I'm just going to recenter the ruler right here. And it looks as though, so that's 180 centimeters plus what looks to be about 140 centimeters, maybe 142 or so. So 142 centimeters plus 180 centimeters is going to give us 322 centimeters. So that's about the distance between the lamp and the screen. Now, in doing this, we've also just kind of directly calculated Q, though you should still write down the image distance being 322 and show the calculation Q, which is going to give you 142. I can show you that over here. So on your lab report, at least once, show the calculation Q equals x sub I minus x sub c. And in this case, we've got x sub I being 142. That's, or sorry, 322, my bad. 322 minus the position of the lens, which is 180, which is about 142. Should be equal to Q here. So you're going to be show this at least once on your lab reports, and we'll be good to go. So now you have P, you have Q, you have x sub I, and you have x sub naught. So go ahead and make sure you fill all of those in here, and then we'll be using those to calculate 1 over P and 1 over Q a bit later. All right, so the next step, it says to move the lens forward 20 centimeters from where it was. So now the lens is positioned at 200 centimeters away from the lamp, and if we measure that real quick, you can see that's about the truth, because this is ostensibly like a 2-meter stick in this scaling. Now, finally, it says to record that position, so go ahead and record 200 centimeters down for x sub c, and then calculate P based on that, and enter it into the table as well. Now it says to repeat steps 3 through 9 until you have filled out the measurement of distances and calculated values in the data section. So we're just going to repeat the measurement that we just made 1, 2, 3, 4 more times, because at this point this line, and if you've done it so far, this line should also be filled in. So we're going to do that 4 more times. I will kind of speed through it, but hopefully you should be able to pick up the data as we go. Okay, so we know that the lens is now at 200 centimeters, so that's x sub c. We're going to move the screen until the image focuses yet again. There we go, and just check that it's correct with marginal rays. Awesome. Looks good. Now we're going to measure the distance from the lens to the screen. And in this case, it looks like it's about 130 centimeters. So a little bit closer to the lens than it was last time. So we know that the lens is 200 centimeters away from the light because we just measured that. So this is 200 centimeters plus about 130 centimeters gives us a lens or a screen distance of about 330 centimeters. So go ahead and mark that in your little table here. So you got 200 centimeters for your lab position, or for your lens position, and about 330 centimeters for your screen position, and then you can calculate P and Q based on those. Moving forward, it says to move the lens 20 centimeters to the right. So now the lens is 220 centimeters, so feel free to plug that into your data table down there. I'm going to refocus this screen real quick. There we go. So you'll notice every time we move the lens, we have to move the screen to adjust for it, right? That's kind of the idea. And let's try to make sure that everything's on the same plane here. That was my bad. I didn't mean to pull it down. All right, so we've refocused it here. I'm going to turn off the rays. We're going to measure the distance between the lens and the screen. Now this time, it looks like we're at about 125 or so centimeters. So, yeah, so about halfway between 120 and 130 gives about 125. So now we know the lens is at 220 centimeters plus about 135 centimeters. Gives us a screen position of 355 centimeters, I believe. And as long as we've made all these measurements correctly, you should be able to plug that into your image distance, or sorry, your screen position and your lens position. So again, our lens here is at 220, and our screen was 125 away from that. So if that's the case, then it actually should be at 345. Sorry, I had an extra 10 somewhere in there. So again, 125 plus 220 gives you 345 for your screen distance. So plug that into here, and we'll move forward. So we're going to move the lens forward 20 centimeters again. So now the lens is at 240 centimeters, and I'm going to refocus the light on the screen. That looks good to me. Let's go ahead and calculate or measure the distance here. Okay, so we got about exactly 120 centimeters. So here, the lens is at 240. So plug that into here, and then plug 220 plus 120, so about 340, right? 220 plus 120 gives you 340, or 360, sorry. Can't do math in my head today. 360 centimeters for this screen position right here. And then you can calculate P and Q based on those. And moving on to the last measurement, so you should only have one more row to go in your data here. Going to move this forward 20 centimeters. So now the lens is centered at 260 centimeters, and then we're going to refocus the light once again on the lens, or on the screen here. That looks good to me, and we're going to measure that distance. So that looks to be about 115 centimeters. So we know that the lens is at 260 centimeters plus 115 centimeters gives us a distance for the screen of about 375 centimeters. So go ahead and plug in 260 centimeters here, 375 centimeters here, and then you can make your calculations for P and Q for each of those 5 scenarios, and then you can calculate 1 over P and 1 over Q based off of this table, and you should be free and clear to answer these data analysis questions, which I will leave up to you. Of course, if you have questions, feel free to email me. Feel free to rewatch this video as many times as you need, be it at half or a quarter speed. Apologies if I went a little quickly. I know I'm pretty new to this, so hopefully this was helpful. As always, just email me if you have any questions, and thanks for watching.